Okay, so today we're going to take a look at related rates. It starts on page 21. But before we get into the related rates, I want to review implicit differentiation. So implicit differentiation we did back when we had, let's see, like x squared plus y squared equals 9. And then we said, okay, well, let's take dx of both sides. And then remember, anytime we encounter something other than x, we have to do the derivative of that with respect to x. So now what we want to look at, related rates, are derivatives with respect to time. So that means we're going to do d dt of both sides of the equation. So I'm going to take a look at the first one. We want to do d dt of 2x plus y squared equals d dt of 7. Now, before when we did this, we did d dx, and anytime we encountered something with x, we just did the derivative like normal. But now, since we're taking the derivative with respect to t, we're going to have basically in every situation, it's going to be d of whatever the variable is over dt at the end. So the derivative of 2x is 2, but then we have dx dt. Plus derivative of y squared is 2y dy dt. And then on the right side, that's a constant, so that just becomes 0. Now, when we actually do the rates problems, we are going to substitute values in here. But we'll just leave it like that for now. Okay. Over here, we want d dt of sine of y equals d dt of x cubed minus x. So here we're going to have to do cosine of y dy dt, and then on the right side we have 3x squared dx dt minus 1 dx dt. Okay, so like the optimization problems, related rates have a number of steps involved. And part of the difficulty with these is, you first need to understand the question, understand the problem. So what we're going to do is we're going to identify the variables whose rate of change you seek, and the variable or variables whose rate of change you know. So anytime we think of a rate, we think of something that's changing with respect to time. So if they give us something in feet per second, that's a rate. They give us cubic inches per minute. So a rate is a unit of measure per unit of time. So that could, again, be meters per second, could be foot per hour. Next is where we want to develop a mathematical model of the problem. Sometimes it helps to draw pictures, label the parts, okay? One of the things we want to be able to distinguish is constant quantities. So in other words, things that are not changing. Next, we're going to write an equation relating the variables, the ones that we know, the ones that we're looking for. And then step 4, we're going to differentiate both sides with respect to time. And then we're going to substitute our values for any of the quantities that we know. And finally, interpret the solution. Okay, so just here's some examples of what related rates would look like. So sometimes they'll say a change in the horizontal distance, so we'll call that dx dt. This is just notation. And then here's some sample units, inches per second, meters per minute. dy dt, maybe that's a change in the vertical distance. dz dt, dr dt, change in the radius. dh dt, change in the height. dA dt, change in the area. And then we get to stuff with the area. You'll always see square units per unit of time. Surface area is area again, so square centimeters per unit of time. Change in volume, that's cubic measure per unit of time. Okay, so let's take a look at example 1. And actually, for some reason, it didn't, the actual question is missing, so you're going to have to write that down. A ladder is slipping down a vertical wall. The ladder is 13 feet long, and the top of it is slipping at the constant rate of 2 feet per second. At what rate is the base of the ladder slipping away from the wall when the base is 6 feet from the wall? So, picture, here's a wall. Here's the 13-foot ladder. And so as it's slipping down, the base of the ladder right here is slipping out. So let's take a look. What rates do we know? Well, we only know one rate, 2 feet per second. That's the rate that the top of the ladder is slipping down. So here's y is representing that vertical distance. So we know dy dt. And since the rates can be positive or negative, so we think about, is the distance getting bigger or getting smaller? Well, as it's going down, that vertical distance is getting smaller. So it's a -2 feet per second. Now, what are we looking for? We're looking for the rate that the base of the ladder is slipping away from the wall. So that's our x. That's going this way. So we are trying to find dx dt. Anything that we know is constant? Well, the actual ladder. The ladder is 13 feet. So that doesn't have a variable. So we'll just put, since this is x, this is y, we'll say z is 13. Next up, we want to relate the three variables. Well, notice, what kind of triangle do we have here? This is a right triangle. So how can we relate right triangles? Well, we have two things. We can either do Pythagorean theorem, or we can do trigonometry, SOHCAHTOA. But since this one all has to do with the sides, and I notice there's an angle theta, but it's not really referring to that angle in the problem, we're going to use Pythagorean theorem. So x squared plus y squared equals z squared. This is how we relate the variables. Now, what we want to do is plug in any constants. Well, we said the only thing that's staying constant is the 13, so I'm actually just going to replace z squared with 13 squared. Next step, we want to do d dt of both sides. This is the important part because it's going to see how the rates relate. So the first one, x squared, that's going to become 2x dx dt plus 2y dy dt equals, we don't care what 13 squared is, but when we take the derivative of a constant, that's 0. Now, in the directions that I had you guys write down here, we said, at what rate is the base of the ladder slipping away from the wall when the base is 6 feet from the wall? The reason we didn't plug that in is because that's not constant. This is changing. So now what we want to do is we want to say right here, at this instant, so when the base is 6 feet away, so when x equals 6, okay, what happens? Well, if x is 6, remember, if z is 13, we can figure out y. So we have 6 squared plus y squared equals 13 squared. So we get y is square root of 133. So now I think I have everything that I need to substitute in. So I have 2 times x, so that's 6. dx dt, that's actually what we're trying to find, so I'm just going to leave that, plus 2 times y, which we said is root 133, and then dy dt is -2. So I have 12 dx dt equals, and then this will be negative 4 root 133. Move it to the other side. Next, we're going to divide both sides by 12. So I actually just want to a decimal approximation here. And I get 3.844. So now we want to interpret the solution. So what does this mean? This means that the base is slipping away at 3.844 feet per second. Okay, example 2. A spherical balloon is inflated with helium at the rate of 20 cubic centimeters per second. So right away we see that's a rate, and it's cubic centimeters per second. So this is actually a dV dt. Okay. Now I'm going to give you, and don't worry about on the test, I will give you the volume and surface area formula. The volume of a sphere is 4/3 pi r cubed, and the surface area is 4 pi r squared. So part A says, how fast is the radius increasing when the radius is 4 centimeters? Well, so notice what I gave you was volume. So we're actually, for the first part, I'm going to use the volume formula. And we want to know how fast is the radius increasing. So this, we're looking for dr dt. Right at the moment when the radius is 4 centimeters, but just be aware that this is not a constant. So since I was given dV dt, I'm going to start out with V equals 4/3 pi r cubed. And I'm going to, again, since I have no constants, I'm going to go right to doing d dt of both sides. On the left side, I get dV dt. On the right side, so I get to use power rules, so the 3 goes in front, so that would be, the 3's would cancel, so I get 4 pi, and then r squared, and then dr dt. Now we get to substitute some values in. So dV dt I was given, that's 20. 4 pi, that's just a constant, that's a coefficient, excuse me. Now r squared, so now we can plug in when r is 4. So 4 squared. And dr dt, that's what I'm looking for. So I get, that's 4 squared 16 times, so 64 pi. So I want 20 divided by 64 pi gives us 0.099. So how fast is the radius increasing? Radius is increasing at 0.099 centimeters per, and we have seconds. All right, how fast is the surface area increasing when the radius is 4 centimeters? So how fast is the surface area increasing? That's a ds dt. So now we're going to work with the surface area formula, which is S equals 4 pi r squared. And I want to do d dt of both sides. So we get ds dt on the left side, and then on the right side we get 8 pi r dr dt. Well, we found out from the previous part what dr dt is, right? Dr dt. So we can substitute in 8 pi, again radius is 4, and then dr dt is 0.099. So we're going to plug all that in. So we get ds dt equals 9.953. So the surface area is increasing at 9.953, and this is going to be square centimeters per second since it's area. Okay, so go ahead and work on your homework, and we will go over questions next class.